NASA's James Webb Space Telescope has hardly opened its eyes, and the universe is new, more mysterious, more beautiful than humanity's dreams. And all these little dots are stars?
All these little dots are galaxies, some of which are bigger than our own.
Breaking news. We may have just found potential evidence of intelligent life beyond Earth.
This is a huge discovery, and we think that it's a huge discovery. And that's the most exciting piece of this telescope, of this remarkable instrument we put in space, is finding things that we didn't expect, that we can't explain, because that means that we have to revise our understanding of the universe.
Well, JWST is so phenomenal that if you spend enough time, you could probably find any galaxy that ever formed in the universe. It's really that powerful.
Pluto, a far-off and cryptic planet, was once viewed as a component of our neighborhood planetary framework. However, ongoing, amazing explanations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have pushed Pluto back into the spotlight. They suggested that this frosty world may be on a potential crash course with Neptune. How might this be within the realm of possibility? And what results would such a devastating event have? Could this be a captivating, grandiose peculiarity? Or is there something else to this approaching fiasco? Join us as we delve into the potential consequences of a Pluto-Neptune crash. Once classified as a planet and later renamed as a dwarf planet, Pluto remains a subject of interest in the vast universe. This is evident from the new hypotheses by eminent experts. Pluto's orbit closely converges with Neptune's, which has raised concerns among astrophysicists, including Neil deGrasse Tyson and Michio Kaku, who warn of a possible catastrophic impact between the two, with significant repercussions for Earth. But how could such an event occur? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes a staggering 248 years to complete a single orbit. Since its discovery in 1930, Pluto has not even completed a full revolution yet. The intrigue doesn't end there. Pluto's orbit is particularly elliptical, deviating significantly from the nearly circular orbits of the major planets. A particularly fascinating feature is its tilt, 17 degrees to the ecliptic plane, making its path noticeably slanted compared to the other planets. This inclination and eccentricity introduce additional layers of complexity to its orbit. One of the most exceptional aspects of Pluto's orbit is how it intersects with Neptune's. For about 20 years during each orbit, Pluto comes closer to the Sun than Neptune, defying what one might expect based on their positions in the planetary system. This raises the natural question: why hasn't Pluto crashed into Neptune? The answer lies in the gravitational interactions of various planets. The study of Pluto's orbit began following its discovery as astronomers sought to understand its unique path. Unlike most planets whose orbits lie close to the ecliptic plane, Pluto's orbit stands out due to its steep inclination and eccentric shape. The mystery deepened when scientists realized that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit, despite these complexities, demonstrates the intricacies of celestial mechanics. The three-body problem in space refers to the challenge of calculating how three objects, such as Pluto, Neptune, and the Sun, interact with each other gravitationally. This is similar to predicting how objects will move based on their initial positions and mutual gravitational influences. In Pluto's case, the problem illustrates how its orbit, Neptune's gravity, and the Sun's pull all interact in a complex manner. Astrophysicists highlight terms like non-synchronous libration, orbital precession, and the VZK oscillation to explain this phenomenon. Non-synchronous libration refers to how, whenever Pluto crosses Neptune's orbit, it is at least 90 degrees away from Neptune. This spatial separation is crucial in preventing a collision. Orbital precession refers to the slight vertical movement of an orbiting body. For Pluto, this means that when it approaches Neptune or another large planet, it is positioned above their orbital plane, providing an additional safeguard. Another significant factor is the VZK oscillation, which describes how Pluto, Neptune, and the Sun's gravitational forces influence each other. This oscillation helps maintain Pluto's orbit, preventing any erratic movements that could lead to a crash. Despite Pluto's seemingly irregular path, this oscillation stabilizes its motion over long periods, revealing that even chaotic-looking systems follow hidden patterns and rules. These factors help keep Pluto's orbit stable, ensuring that it does not collide with Neptune or drift too far off its course. The three-body problem is crucial for understanding changes in these orbits and the interactions between celestial objects. Studying this helps scientists learn more about Pluto, our solar system, and even distant stars and planets. Mathematical simulations during the 1980s revealed that, despite these stabilizing effects, Pluto's orbit is unpredictable. Even small variations in its initial conditions could lead to significant changes over centuries. However, Pluto's orbit has been found to remain stable over extremely long time scales. Further studies have helped us understand how Neptune, Jupiter, and Saturn influence Pluto's orbit. There is a unique relationship between Neptune and Pluto. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This relationship helps keep Pluto's orbit stable. Jupiter's immense gravity also plays a crucial role in stabilizing Pluto's orbit, preventing it from drifting too far into Neptune's domain. Saturn's gravitational pull adds another layer of stability. These findings suggest that Jupiter, Saturn, and Neptune work together to ensure Pluto's safe passage through space without encountering any major issues. Without these gravitational interactions, the solar system could be a much more chaotic place, where objects like Pluto might crash into other planets or be ejected from their orbits, triggering a chain reaction of events. Understanding its orbit is essential, especially when discussing the possibility of it colliding with Neptune in the future. This also gives us a clearer understanding of the dynamic nature of our planetary system. The case of Pluto highlights how even the most complex celestial mechanics follow precise and predictable laws, keeping the solar system in a delicate but stable balance. The grand cosmic ballet. How Pluto and Neptune avoid collision. Pluto's orbital stability is a result of intricate gravitational influences, primarily driven by its resonance with Neptune. While the idea of a potential Pluto-Neptune collision might seem alarming, the reality is far more complex. Astronomical studies have shown that their orbits are locked in a protective mechanism known as a mean motion resonance, ensuring that despite their paths crossing, a direct impact is virtually impossible under current conditions. The protective role of orbital resonance. As mentioned earlier, Pluto and Neptune share a 3:2 orbital resonance, meaning that for every 3 orbits Neptune completes around the Sun, Pluto completes exactly 2. This synchronized movement prevents their paths from leading to a catastrophic collision. In addition to this, the gravitational influences of Jupiter and Saturn help stabilize Pluto's orbit further. If not for their presence, Pluto's trajectory could have been significantly more erratic. Could an external force disrupt this balance? Despite this long-term stability, astronomers continue to explore the possibility of external factors influencing Pluto's trajectory. These include 1. Passing stars. If a rogue star were to pass close to the solar system, its gravitational force could perturb Neptune's or Pluto's orbit. While highly improbable, such interactions have been proposed in theoretical astrophysics. 2. Undiscovered planetary bodies. Some scientists speculate that a yet undiscovered planet 9 or another distant celestial body could exert a subtle but cumulative gravitational effect on Pluto's orbit over millions of years. 3. Galactic tides. The Milky Way itself exerts a weak but constant gravitational pull on objects in the outer solar system. Over extremely long periods, this could induce minor orbital shifts. What if Pluto did collide with Neptune? If hypothetically, Pluto's orbital stability were to be disrupted and a collision with Neptune became inevitable, the consequences would be staggering. Pluto, with a diameter of about 2,377 kilometers, is significantly smaller than Neptune, which is 49,244 kilometers across. However, the impact would still be catastrophic, potentially shattering Pluto into countless fragments, forming a new ring system around Neptune, altering Neptune's orbit, potentially affecting other planetary alignments, disrupting Kuiper belt objects, sending debris deeper into the solar system, creating a cascade of collisions, possibly affecting Neptune's moons. However, as current models indicate, such a scenario is astronomically improbable. The future of Pluto's orbit. For now, Pluto remains safely locked in its stable orbit, and researchers continue to refine their models to predict its movement over the next millennia. The study of Pluto's orbit is not just about planetary dynamics. It offers key insights into the evolution of the solar system and the mechanisms that maintain cosmic order. With future space missions and advancements in computational astrophysics, we may uncover even more hidden complexities in the dance between Pluto and Neptune. Until then, the dwarf planet continues its slow, solitary journey around the Sun, maintaining its place as one of the most intriguing celestial objects in our solar system. Most apparently temperamental circles can arrive at a condition of harmony through the mind-boggling transaction of gravitational forces and orbital mechanics. It also highlights the importance of consistent perception and research to better grasp our place in the universe. The investigation of divine bodies frequently leads us to confront their peculiar behaviors, and Pluto's orbit is a perfect representation of this strange nature. The idea of orbital turmoil, which refers to the sensitivity of a celestial body's orbit to its initial condition, is clearly demonstrated by Pluto's path. Even slight changes in its position or speed can lead to dramatic changes in its long-term orbit. Mechanized simulations have been instrumental in helping researchers understand Pluto's movements in space. These simulations use advanced mathematics to model the gravitational interactions between Pluto, Neptune, and other bodies in the solar system. By tweaking small details in the simulations, scientists can see how even minuscule shifts can significantly alter Pluto's trajectory. In the late 1980s, these simulations revealed fascinating insights about Pluto's orbit. While stabilizing factors like asynchronous libration and orbital precession help maintain stability, Pluto's orbit can still be unpredictable if its initial conditions vary even slightly. However, despite the apparent chaos, Pluto's orbit remains stable over vast timescales, such as billions of years. This suggests that, despite the seeming unpredictability of Pluto's journey around the Sun, there is an underlying order to it. Predicting the movements of celestial bodies, particularly those with irregular orbits like Pluto, is an enormous challenge. The inherent unpredictability of these systems means that long-term predictions are fraught with uncertainties. While mathematical models are invaluable in understanding and forecasting the future movements of celestial bodies, they also highlight the limitations of our predictive abilities. These models rely heavily on the accuracy of the initial conditions, and even the smallest error can lead to vastly different outcomes. The chaotic nature of planetary orbits, such as Pluto's, serves as a reminder of the ever-changing dynamic nature of the universe. While we have made incredible progress in understanding space, Pluto's case demonstrates how much there is still to discover. The gravitational effects of the giant planets on Pluto's orbit provide valuable insights into the broader workings of the solar system. They reveal how the positioning of each planet can significantly impact the stability and trajectory of other bodies within the system. So why have prominent astrophysicists recently raised concerns about a possible collision between Pluto and Neptune? Despite all these forces working to keep the two planets from colliding, Neil deGrasse Tyson, a leading astrophysicist, offers a unique perspective on the mysteries of our solar system, particularly Pluto. Tyson, who played a role in Pluto's reclassification as a dwarf planet, provides valuable insights into the evolving understanding of celestial mechanics and the public's renewed interest in overlooked aspects of space. Tyson sees Pluto's reclassification not as a demotion but as a necessary adjustment based on the expanding knowledge of the diverse objects orbiting the Sun. He believes that the complexities of orbits like Pluto's reflect how much is still left to explore in space. The ongoing fascination with these questions fuels the excitement of space exploration. Despite Tyson's optimism, his concerns about Pluto's potential collision with Neptune suggest that there are still many unknowns regarding Pluto's orbit. Will Pluto crash into Neptune, or is this just another instance of confusion in the ever-changing universe? Only time and further research will provide an answer. For now, we are left with a heightened curiosity about how little we truly know about our own solar system. We continue to study these celestial phenomena with the intent of uncovering the secrets that lie beyond. The possibility of a Pluto-Neptune collision raises more questions about the mysterious and captivating universe in which we exist. The prospect of an impact between Pluto and Neptune challenges our conventional understanding of planetary stability, especially given the current relative characteristics of their orbits. Considering Pluto's location on the outer edges of the solar system, far from the major planets, and Neptune's status as a gas giant with a strong gravitational field, the implications of such a collision would be significant for our understanding of gravitational interactions and the evolution of the solar system. To understand the dynamics of a potential impact, one must first consider the composition and properties of Pluto and Neptune. Pluto, despite being a dwarf planet, is composed of various substances believed to exist in a frozen state due to the extreme cold of the outer solar system. Its surface is covered with nitrogen ice, and its atmosphere consists mainly of nitrogen, methane, and carbon monoxide. In contrast, Neptune, a massive gas planet, is made primarily of hydrogen, helium, and other lighter elements, with a thick, deep atmosphere. A collision between these vastly different bodies would significantly alter their structure and behavior, potentially creating an event visible across vast distances. What makes this hypothetical impact particularly intriguing is the influence of other bodies in the solar system. While Neptune's gravity plays a key role in stabilizing Pluto's orbit, it is not the only factor at play. Jupiter, with its immense mass and strong gravitational pull, also has a stabilizing effect on Pluto's orbit, preventing it from drifting too close to Neptune. Saturn's gravitational influence further complicates the dynamics of the outer solar system, making a catastrophic event between Pluto and Neptune highly unlikely. However, despite the apparent risks, ongoing research has shown that the relationship between Pluto and Neptune is far more complex than a direct collision course. The gravitational resonance between Pluto and Neptune, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3, creates a cosmic lock that prevents them from directly colliding. This resonance is a crucial factor in ensuring that, while Pluto and Neptune's orbits do cross in the vastness of space, they have never resulted in a direct collision.